Hello and welcome to SDN Tech Forum. In this video, we are going to talk about IP or Internet Protocol. Internet Protocol belongs to network layer in OSI model. It's a layer 3 protocol, and as part of technical definition, we can say that IP address is a numerical representation that uniquely identify a specific interface on the network. But as we are familiar, IP addresses are everywhere. Your mobile phone, your laptop, your PCs, if you connect to internet or even for LAN users, they all have IP addresses. So it feels like that each device have just one IP address, but which is not true. A single device may have multiple IP addresses, and this statement is even more true in case of IPv6. For IPv4, you can still live with one IP address, but again, IP address essentially denote a network interface in the specific interface in the network. So what is IP address? IP address is a 32-bit long value. That means you can have 2 to the power 32 unique IP addresses, which is nearly 4 million IP addresses. But and there are, as I discussed, there are two categories of protocol today: IPv4 and IPv6. So IPv4 is the the initial one, and as IPv4 started hitting the upper limit of this 4 million IP addresses, there came another protocol which has some more enhancement, which we call IP version 6. So IP version 4 and IP version 6. And in this video, we are going to talk about IP version 4 only. So 4 million unique IP addresses you can get, but it's not, you cannot use all 4 million. So total usable address pool is reduced by various reserve addresses, and we'll see what are those reserve addresses and what are their use case. IPv4 address is typically expressed how you can see a IP address. It's expressed in dotted decimal. So 4 octets, that means 8 bits, and I have an example here. So IP address looks like this, may look like this: 192.168.10.1. That means the each for 8 bit or octet can range from 0 to 255. All right. And IPv4 address composed of two parts. So the first part specifies the network part of it, and then second part specifies the host. So a subnet mask comes into the picture when we talk about network part and a host part. So we'll see what is a subnet mask next. A subnet mask. Subnet mask, a single IP address identify both a network and a unique interface on that network. A subnet mask can also be written in dotted decimal, just like IP address. Subnet mask can also be expressed in dotted decimal, and it actually tells you which is the network part and which is the host portion of it. So when expressed in binary, any bit set to 1 correspond to the bit IP addresses network side, and bit set to 0, they are host. So for example, you can see that and this is a subnet mask 255.255.255.0. It is a class C subnet mask, or we can say 888.24/24 subnet mask. So now, as we talking about IP address classes, so what are those different IP address classes? You can see here. So today, with variable length subnet mask or CIDR, you can have IP address with any mask, any kind of subnet mask. But initially, the IPv4 address were broken in 5 class based on their subnet mask ranges. So you can see that class A runs from 1.0.1 to 126.255.255.254. Class B starts from 128 to 192. Class C from 190 to 223. Class D 224 to 239, and 240 to 254. And all the purposes are also here. So class A, it can support these many host and these many network. You can use any IP subnet calculator to calculate this. And class D, it is reserved for multicast group. Class E, reserved for future uses and research and development purposes. So these are the 5 different classes of IP addresses. Now, so IP addresses are unique, right? That means they are routable across the internet. So that means if you have a unique IP address, someone can identify you and reach you via the network if it is advertised out to the internet. But what if you are using for personal use or lab purpose, or you have a home LAN setup? For that, or a big organization where thousands of employees are working, right, and they need to communicate it to each other. So for those purposes, we have private addresses. That means these are reserved for private networks. So the same company A may choose to use the private address from 10.0.0.1 to 10, so class A series of IP addresses. Company X may or can also use, and company Y may also use, without any stepping into each other, because this is confined into a private domain. And so these are the private addresses reserved. Basically we say that 10.0.0/8, and we say 172.16.0.0/12 and 192.168/16. But other than this private addresses, and there are some addresses which are set aside for specific uses. So this is a very good illustration here. You can see. So it also highlight the private use network, as I mentioned earlier, 10.0.0/8, 172.16/12, 192.168/16. These are private, but other than that, you can see that there are a lot of network like 198.18/15. It is used for benchmark testing, and some are used for documentation purposes like 198.51 or 203.0 testnet. So these are in books and in literature you will find a lot of IP addresses mentioned with this reserve range, because they are reserved for the specific purposes like testing and documentation. Now let's go to understand IPv4 header, how a IPv4 header looks like. So IPv4 header is minimum 20 byte. You can see on the right side here. So each row is 4 byte long. That means 32 bit. 4 byte, 1 byte is 8 bit, 4 byte is 32 bit, and you have 1, 2, 3, 4, and 5 rows minimum. IP options, these are optional, but bare minimum you should have these 5 rows. That means 4 into 5, 20 bytes of 20 byte long IP header. That should be at minimum. And now this we can see what are the different fields in IP header. So we go row by row. So you have version, 1 byte of version, 1 byte of IHL, which says header length. Header length will tell you how many rows you have. So if we don't have any option, header length is always set to 5. That means I have my header 5 row header. Version always set to 4 for IPv4. Type of service is very important. It is used for QoS, layer 3 QoS. So one byte of type 4, actually two byte of type of services, and they are basically used for QoS and DSCP. So these fields are, and then you can see the next is identification, flag, fragment. This is very important. This is especially dedicated for fragmentation, and it tells you how when a IP packet is fragmented, how they are handled, how they are reassembled. So we will have this in our demo, and I will show you how the fragmentation and reassembly work live in our demo. Then you have time to live TTL field, which is to avoid infinite loop. So TTL is set to some value, and when your packet goes from one hop to another hop, the TTL is decremented by 1. and if TTL goes to 0, the packet is just dropped. So it prevents you some sort of looping, right? So that there is no infinite loop going on in your network. Then the protocol field, as we discussed in earlier video, so this protocol field here denotes what is my upper layer protocol, what kind of payload I'm carrying. So you can see that there are certain designation, like if it is protocol set to 1, that means we are carrying ICMP. If it is 6, then it is a TCP payload. If it is 17, that means we are UDP type, and all those. Header checksum is just for error correction and checksum, and then comes source address and destination address. So what is my source address, what is the IP address for my interface, and where it is going, destination address. So it is here you can see like a very nice description of each field, and we will see all this when we go to the demo. Now I want to have a special mention on fragmentation and reassembly. This is quite ignored field even in books and documentation, but it is very important. So as you have seen that this row, the second row, basically deals with fragmentation, and there are three fields: identification, flags, and fragment offset, and their purpose is very clear. I'll tell you what is that. Identification, this field provides the number used to identify packets that belong together to the reassembly. So if you have very large packet and you break it down into like 2 or 3 different IP packets, there should be some sort of identification which says that yes, all these 3 packets, they belong to one single large packet, right? So that's why identification come into picture. And then there is a flag field. Flag is like control bits. So this is a 3-bit field. 1 bit, bit 0 is reserved, but remaining 2 bit, it tells if do not fragment is set. So if do not fragment is set, that means it is telling the router that hey, this IP packet is not eligible for fragment. So if you cannot handle this big packet, just drop it, but it doesn't allow it to fragment. And bit 2 is set for more fragment, that say yes, you can fragment it, and there are more packets coming behind me which belongs to the same flow. And when more field is set to 0, that means I'm the last packet. Fragment offset is like it denotes the chunk, right? So when you break down a single large packet into 2-3 packets, so when it comes to reassembly, how will identify that which packet should come first and which come second and which come third, right? So fragment offset tells you that. So it says that okay, this is the first packet, and this is 1480 byte long, and then the second packet start with 14 multiple of that. So this is how with the number you can sequence them properly and reassemble them. So we will see all these when we go to our demo. What I'm going to do in my demo is having 2 Ubuntu based PCs. They will generate a IP packet, ICMP based packet. We'll see the ping request and reply, and I'm going to use a large IPMTU. So we will bring fragmentation in picture and see how fragmentation is handled. So we will actually drill down into the IP packet and fragmentation and reassembly in our demo. So stay tuned. Thank you. Hello and welcome to IP Internet Protocol demo. In this video, I'm going to run a IP ping between 2 Ubuntu machines, and I'm going to show you the different content of IP header, and we will see how the fragmentation and reassembly happens. So this is my Ubuntu machine, which has IP address on my 192.61.25. This is my IP address, and subnet mask is here, mask length 24. And as you can recognize, this is a private IP. So what I'm going to do, I'm going to initiate a ping to the next Ubuntu machine, which is in the same LAN, and this time I'm using a ping which send ICMP request and get ICMP reply back if the host is reachable. And I'm going to add an attribute called -s, lower caps s, and that means I'm going to send a packet size of 3100. So by default it send 1500 of packet size, but I'm going to send 3100 just to create fragmentation. So on my router side I have 1500 as MTU. So once my router receives 3100 size of packet, it cannot handle that, and it is going to fragment that packet, and it will forward the fragmented packet, and then the reassembly will happen. So let's initiate the ping, and I have a Wireshark capture going on. So you can see that I initiated a ping with packet size 3100, and it is taking 3108, and 3108 is 8 byte is for ICMP header. All right, let's go back, and here I'm capturing already. So now I'll walk you through the ICMP echo and reply. So these are the first packet, ICMP request and ICMP reply. You can see 61.25, this is my source, sending to 6193. So ICMP request goes to that host, and then in turn we are getting reply back from 93 to 25, and this is a reply. So let's start looking into what goes in the packet. So this is the first packet, and let me start from the beginning. So Ethernet is like a source and destination address, and then we are interested in IP, so let's expand the IP protocol. So you can see the IP protocol versions is, since this is IPv4, set to 4, and then you have source address and destination address on high level, but we'll drill down into the packet and look at each field. So version is set to 1, then you have header length, which is set to 5 into 4, 20 byte, so because we don't have any optional field. And then we have differentiated service field or type of service field. So if you are not using any kind of QoS, it is all set to 0. That means best effort service. And then you had total length field. If you recall from the technical discussion, the total length is 1500. Identification flow, the second row, which is responsible for fragmentation and reassembly. Please pay attention, and you can see that identification is set to 37904, and for entire packet this identification should remain same, so that we can identify that they all belong to one flow. Then the flags, bit 0 is reserved, not used. Do not fragment is not set, that means router is okay to fragment the packet. And then 1, it is set to 1, that means you can expect more fragment coming behind this. Then you have time to live, TTL field, which is set to 640, which is sometimes used for loop avoidance. Protocol, so protocol field tells you the upper layer protocol what you're carrying. In my case, since we are running ping, it is ICMP, which is protocol number 1. Then header checksum for error correction, and finally you have source address and destination address. You would like to take a look at data 1480. So we initiated a 1500 byte packet, but then the actual payload is 1480 because we initiated a 3100 byte packet, but then it get fragmented, and the maximum fragment size could be 1500, but the data is here shown is 1480 because you have to take into account of 20 byte of IP header. So 1480 plus 20 byte of IP header makes a 1500 byte of packet. Okay, so this is the first fragmented packet. Then you have the second fragmented packet. They should all look same. That means your source and destination, version, all those fields looks exactly same. What will look different? So let's pay attention on fragmentation field. Okay, so identification is again 37904. If I go back to the earlier packet, it is also 37904. So identification doesn't change. Identification has to be same to denote that they are fragment of the same original packet. So identification is same. Again, more fragment bit is set, that means there is more fragment coming. And look at the fragment offset. So the next fragment offset is 185. What was the earlier fragment offset? 0. Okay, then final packet, which is like a small packet, because 1500 make 3000, and then the final packet should be like a small one, so 182. And you can see that more fragment bit is now clear. That means you should not expect any more fragment packet for that, and you are good to reassemble. and the fragment offset is set to 370. So this is the final packet, and all of the information will be same. And we can dig into the little bit into the lower side also, which is ICMP. So you can see that this is ICMP code 8, that is echo ping request, and code is 0, and checksum and everything so look correct. So this is for the upper layer thing. So you can see that only at the final packet Wireshark was able to recognize that this is a ICMP packet, and it is giving us the ICMP header detail. In prior packets you didn't have those details. Now let's look at the ICMP reply, what reply we are getting. So let me pull it, and you can see a reply is coming from 193 back to 25, version field set to 4, total health header length is 5, that means 20 byte. We are not using type of service, DSCP is set to 0, total length 5200, and identification flag changes, you see 11501, because this is the different packet. And again, since it is a fragmented, so you have the bit 2 set, that means you should expect more fragment, and fragment bit offset is 0, that means this is the first fragment, and it has the ICMP underneath. And the same thing, you can see that fragment identification doesn't change, it is still 11510, and more fragment bit is set because you are expecting a smaller packet behind it with fragment offset 185. And finally the last packet, echo reply, and in this fragment offset is set to the last value, and also more fragment field is clear. So this is how the fragmentation and reassembly handled. And ICMP code, you can see now the code changes, the type changes from 8 to 0, which is echo reply, and everything looks good. So now you understand the different field in IP header, why they are used, and most importantly how fragmentation is handled and reassembly happens. So I hope you enjoyed the video. Thank you for watching.